Hello everyone, my name is Vassili and I'm going to give a lecture pre-course on module 10, which is called Deep Learning. And I will be giving also at the end a few examples of application of deep learning to biomedical image analysis. So deep learning is something exciting nowadays, and let's go to consider this. So first we start with history and some basic terminology behind. Deep learning and so-called convolutional neural networks, the keyword is convolutional, is a part of machine learning. The symbol of machine learning is something like that, subdividing object in feature spacing and learning that. But sometimes they also consider to be a part of artificial intelligence. So this is more typical for mass media and such kind of information sources. So by the way, the serious neurologists and cognitive scientists who study functioning of real human brain is a bit skeptic about that convolutional neural networks. That's good. I also from that camp. So this is a good engineering tools to solve practical problems using computers, but it's almost nothing to do with the real cognition, what is the key point for brain functioning. Nevertheless, these terms more and more frequently used, I mean artificial intelligence. So convolutional neural networks, we will be saying CNNs, were introduced in 1998-1999 by LeCun. I'm sorry for pronunciation of French. I will never do it correctly. So they were introduced by this gentleman from France, and originally for image classification. And this is the commonly accepted date of appearance of convolutional neural networks and the inventor name. But as any other complicated engineering issue or basic idea, it was not just start from scratch. There were other research in different countries which some way suggest similar solutions, similar architectures, similar things. So that's for instance Fukushima from Japan, who was suggesting similar things in 1980s, but not exactly the same. So let's go. So that's the happy guy who was introducing and a copy of title of his very first papers published, which are introducing really that convolutional neural network at this deep learning approach. Why we call neural networks of this sort convolutional? We call them convolutional because they extensively use the operation of convolution with so-called filters. Filter is nothing what is filtering image, but it's just square-shaped table of numbers, which just apply to pixels to certain region of image and doing so-called convolution. Convolution is element by element multiplication of filter weights, so-called, with image values or feature values and summing up. So if you're a little bit more familiar with image processing, then you perhaps know that what Sobel mask means. So that's example of convolution which is introduced long time ago. So we have this specific filter or table of certain numbers, and we have a piece of images and we multiply them and summing up the result, and that's we end up with one single number. So a convolution resulted in one single number. And this is the basic operation of convolutional neural networks. So let's look at the general structure of convolutional neural networks. convolutional neural networks consist of two parts, major part. One part is convolutional part, which doing convolution. Convolution resulted finally in features, in certain image features, so in feature vector. And so essentially the major goal on convolution of using convolutional neural network is to extract features which are characteristic for original images on the input. And then there is once the feature vector is extracted, then it's typically supplied to the input of so-called fully connected neural network, which is nothing but just classification algorithm. And as a result, on the output, we have this on the output neurons, that circular pieces of neural network called neurons. Traditionally, this is tradition. And for the number of output elements of output neurons, it corresponds to the number of classes we want to devote the image, to put the image to a certain class. So in this case, for this pictogram, I used just two classes. So on the input we have image, on the output we have class which belongs to. That's the result of the whole convolutional neural network. What is important to understand even now in this pre-course, that there are two different modes the convolutional neural network is operating. First mode is training. On training stage, we teaching neural network of real examples from this particular field of application. We teaching by supplying image of something to the input, and we saying which class it belongs to. In very common terminology which is used, like cats and dogs. So we supply the images of dogs and we say this is belong 100% to dog. We supply images of cats, of different sorts of cats, and for each particular image of cat, we say this is the cat. And neural network trying to learn how to produce, essentially convert the original image into class with a certain probability. So it's not saying this is dog, this is cat, but it's saying this 99% of dog and 0.01% of cat. So that's the result. On the output we have probabilities of belonging to certain class. And the learning or training of neural network, convolutional one, is essentially the process of solving global optimization task when as a result we have these weights for every filter. There are plenty of filters inside. So for every filter is somehow fitted so that it's extract the features of certain sort. So that's the first and main mode of functioning of the convolutional neural network, CNN, let me say CNN everywhere else. And this is the most important part, and the second part is prediction. So prediction, once we already properly train neural network to recognize, to categorize images to certain classes, we can use it for prediction. This mode, we supply certain image to the input. This one, it's doing because it's already pre-trained. It's produce feature vector, and then second part just produce probability of this image belong to this class. So that's prediction or simply classification part. So what we have to note here that it's the second part, which is ordinary fully connected neural network, which is known for years and years, which is as old as I. It can be simply removed, for instance. So once we got the feature vector, what is the most important part of CNN, feature extraction, we can take them out of neural network and use any other classifier or use in any other purpose we want. So this is the most important convolutional part, or feature extraction part. This is the most important part of convolutional neural networks. Okay, next, why convolutional CNNs are deep and what they doing. CNNs are part of deep learning because they are deep and they are multi-layer. So we have several, sometimes more, sometimes less, of these convolutional layers. And this is on every layer we have a lot of operation of convolution applied to the original image, and then to simple features, then more general features, then even more general features, etc. So this is the deep optimization problem, the hard optimization problem on the training set, and this is why they call deep. So the second point we have to remember is that it's not necessarily deep learning and convolutional neural networks, CNNs, applied only to the images. Not necessarily. This approach can be also applied to any kind of signal, for instance, speech, which is signal, music, which is sound, all that kind of that sort of spectra just correspond to sounds. To compose music, for instance, and to analyze music, to compare different pieces of music, and for text processing, aimed at extracting semantic from the text, and automatic translation from languages to languages, and for any other purposes where convolution is the basic operation. Of course, you cannot apply it everywhere, but where you need to convolve to analyze certain structures like two-dimensional, three-dimensional, one-dimensional, what is signal, spectra, you can use that. So by the way, this is the spectra which I produced by myself, saying that biomedical image analysis. So this is nice picture correspond to sound biomedical image analysis. Recently, convolutional neural networks and deep learning have demonstrated very impressive results in various applications, and in many cases, this approach just outperforms other machine learning methods, and sometimes they outperform even the best experts working in this particular field. So the illustration could be like that traditional machine learning, having this image on the input, may produce result, this is good. What is certainly not good, this guy certainly with a broken arm, but if we provide that convolution of that features and using convolutional neural networks, the result could be the correct one. So that's, of course, this kind of joke, this is pictogram. Okay, let's consider the basic elements of CNN's architecture. So that's the very key slide. You have to understand this. But now is pre-course. You can just try to understand it and look to additional sources in internet. But finally, we will consider this part in more details in the course itself. So we start with the original image, and we're doing convolution, as I said, element by element multiplication with the filter values and summing up. So this is, here we have 3 by 3 filter. We multiply the value of this filter to corresponding value of pixel. It could be grayscale image, 1 layer, could be 3 layers, RGB image, etc. So we're doing this convolution, and we end up with one single number. So this number corresponds to central pixel of the original images. Then we move to right, in this particular case, move this window 3 by 3 size and doing convolution for the next pixel. And we put it next to this one, and once this row is finished, we go to another row, and row by row we fill in with the layer of results. Then we take another filter and we're doing exactly the same, and we end up with another layer of features. So in this way we produce the very basic features of images. For instance, this filter may express just lines, small line, horizontal line, vertical line, or small corner, and the response of the convolution would be the higher, the more this particular region of image is similar to this filter. So we have a different kind of responses, and if we take this particular pixel for every layer, the maximum value will be located in the layer where the filter which used to produce this layer is correspond to the original piece of image of certain configuration. Once we finish this, and depending on how many different filters we apply, we got this structure, and then when we applying kind of subsampling, we somehow reducing the amount of data and in some way generalizing them. For instance, this is typically done by 2x2, consider 2x2 neighborhoods of these layers, and among that 4 guys we select the most silent. For instance, if we have a line, the elementary is the small one, then the response, the largest response, the biggest response, the greater response will be for filter which is correspond to line, and then we take the maximum. Typically among that 4 guys we have a maximum and transfer the value to the next layer of convolutional neural networks. And we got finally, if we have this, say 10 for instance layers here, so as a result we have also 10 layers here, but it's twice as small as original one, because from every 2x2 we got just one. So we reduce it in space just twice, but we preserve the same number of layers. Then we using this filter. So filter is not necessarily 2D, it could be 3D, like here is 3x3 and by n, could be 3x3 by 10 if we apply 10 filters here. So we convolve with this kind of filter, which is volumetric in this case, and we produce one single value as a result of convolution again. And we applying, once it's done, we applying pooling, subsampling, 2x2 to the next layer, etc., etc., etc. So this is we repeat this process several times, and finally we reduce the whole amount to one feature vector, and that's it. So that's actually simple. There are some details, but we will consider them in a real lecture, but not in pre-course. LeCun introduced this method together with LeCun 5, so-called. This is just name. Neural net architecture, and it is very important. It was just very beginning of new era of deep learning, and the importance of further works for further research and development works was as follows. So this is the architecture, by the way, original architecture introduced by LeCun, and substantial innovations at that time was that image features are distributed across the entire image, because we applied this filtering everywhere. So it doesn't matter if you consider a cat which is sitting somewhere in the frame, so that's convolution will be produced everywhere, and that the image of cat will be somehow considered anyway. The second innovation is that not every particular pixel is going to neural network. It's just regions by convolution goes to the next layer, and this is the way the dimensionality is substantially reduced. So given that image may have millions of pixels, then you can view this the training stage of neural network, like a solving of the system of equations with millions and millions of unknown variables, what is enormously difficult problem. But in this way, the LeCun suggests we reduce the complexity of the optimization task. What is the training stage? What is the most important stage? Because without training, it produces nothing, just noise. So let's go further. So this way, the sequence convolution, non-linearity, so we not consider here non-linearity, it's not very important right now. Convolution, non-linearity, and pooling, these three operations actually constitute the deep learning idea. So next, you have to remember that ordinary neural networks, which are at the end, so we have convolutional part and classification part. Classification is done by fully connected neural network. The classification part is ordinary neural network in this respect. It's introduced well before. So all this innovation just somehow push forward the research in next to LeCun research, but it's not that easy. So from 1998 from original time point to 2010, CNNs were in kind of incubation period. They exist, but majority of people, of researchers in these fields, not really recognize this new idea, not really accept it, including, by the way, myself. So, and very often, if you say neural network, people typically from pattern recognition, they say, "Oh, no more neural networks. We know this. We did it long time ago, so it's not interesting for me." But so it's really very few people only recognize this novelty or this convolutional part of neural networks idea, and they slowly progress in this field. During these 12 years, essentially, almost nothing happened. Very few happened during this period, until it just exploded in 2010 and afterwards. I would say 2012 even. So we consider typical architecture or structure of convolutional neural network, but it's not necessarily exactly like that. It can be changed somehow, adopted to your problem, and certain variations of architecture of neural networks exist. Recently there are many of them, and for researchers who doing this, who is familiar with all these tools, they actually consider very often to introduce their own architecture of neural network. There is software tools, and if you are skillful enough in software, you can introduce your own neural network. So how you can modify existing architecture or just build up from scratch your own? The very straightforward, very simple idea, what immediately comes into the mind, it's you can vary the size of filters. Of course, the largest filter, the most sophisticated elementary structure could be recognized by one single convolution. And of course, you can introduce more different kind of filters. You can introduce 3 filters, 4, 5, 10, 100. Of course, you're paying for this in the computational expenses, which are really high in this case. But nevertheless, you can vary by the size of filters for convolution and number of filters you applied for convolution. The second idea is much more clever. Actually, I like it very much. It's called inception, unusual name rather. And the idea is that we are not just using the same operation to take a piece of previous layer and convert by convolution, convert to another layer, transfer using convolution to another layer. but we can do different ways in the same, between the same layers. We can go with different size of filters, we can go with different architecture, different pooling, subsampling, etc. But this all in parallel. So that I think the key to me, this key idea is that because you don't know how it works, there is no theory, by the way, behind. So you don't know how it works, you can do it in every level, every layer, you can do it in different ways in parallel, and then put together the results and transfer to another layer. So with the hope, some of them will be working well in this particular case of images, in this particular kind of images. So that means we need to go deeper. That's nice actor who said this, and this is why this is inception. In fact, in real life, there are many circumstances when we need to go deeper. So this is one of them. This is a piece of life. So neural networks, convolutional ones, it's just piece of life. So that's the pictogram saying that it could be different operation made, not just one single, but different operation executed in one layer in parallel. So that's another architecture which is called GoogleNet in this case. So LeNet and GoogleNet, which actually exploit, which capitalize on the inception idea very much. So that's examples of convolutions between one and next layer. So 1 by 1, 3 by 3, 5 by 5, max pooling, not just in 2 by 2, 4 pixel by 3 by 3, could be also even more sophisticated structure. So this is why this architecture called sometimes network in network. On every layer of network you have kind of another network. So it's more complicated. It's not necessarily produce better result, by the way. It's definitely takes much more computation on the training period, but it's not necessarily lead you to the better result, by the way. So that's in general how it expressed this architecture, how it can be depicted. If you need more detail, you can go to literature, to internet, you will find. So let's illustrate different trials on convolutional neural networks on computer vision competition, not biomedical research, but in computer vision. So there is so-called ImageNet, which actually made up of free society of people. So they accumulate millions and millions of images, and what is more important, people label them. So at least labeling, that means this is the cat, this is dog, this is tree, this is T-Mac, like my dad, like myself, with a certain flag of some region in the world. This is a mouse, this another mouse, etc., etc., etc. So this is the labeling, simple one, but more complicated. You just manually extract or somehow delineate the object on the background. So it's crowdsourcing. This is made by a lot of people who contribute to that open access database. Finally, we have millions of computer vision images which are not biomedical, and we have tens of thousands, so 20,000 classes. So that's a lot of categories of real life. And on this database, of course, it's good to test new approaches, the power of different neural network architectures, etc. So they start, not we start. We're from the year 2010, and the accuracy, the error of classification error was as high as 28%, what is actually not bad for that time, given that there are so many classes, so many categories. So next year competition resulted in 25.8. error, and then next year 16, then 11, then 7, and that's 6.7, and then finally in 15, 3.57. So that's actually very, very low error for such a large amount of data, for such large number of classes. But you see that number of layers going up and up. So the final neural network architecture, specific network used for that, got 152 layers. That's really very, very deep neural network. So that plot demonstrate how good it to have more layers, but not always. Again, not always. Don't be that straightforward. That's examples of applications which we're doing in our group. So we have a lot of details, as many as you want details. This is work related to automatic detection of lesions, of bad things, which may happen due to different kinds of disease, abnormalities, etc. in human lung, based on computer tomography images. That's the resultant maps which shows where the lesions are, etc. So that's also illustration of this sort. So where the lesion is highlighted with certain probability, it's also segmented. Once it's segmented, the lesion, it can be printed out on 3D printer together with a lung, or maybe just separate one for surgery or for any other purposes, etc. That's another application for cancer diagnosis, based on international data, free access data, histology data. That's our own histology, which is related to angiogenesis process of development of secondary blood vessels within the malignant cancer tumors. That's another service, web-based service, which is under development, by the way, by students. So I'm supervising that group of students who are doing that. They are just third-year students here in Belarus, but they doing well that kind of development. That's another application which is related to screening of lung and heart disease. There are so many of them, unfortunately, may happen, and it's a so-called computer-assisted diagnosis. The goal of computer-assisted diagnosis is to produce this so-called second opinion, which helps doctor to finally decide whether it's normal, abnormal, whether it's belong to this kind of abnormality or that kind of disease, etc. That's an example of automatic detection or automatic diagnosis of lung cancer. By the way, lung cancer is the most dangerous cancer in the world and disease. So in terms that number of people it's killed. So it's number one killer in majority of countries, specifically for men population. So we arrive to the more or less the final point. So life is never that nice. Convolutional neural networks is not the magic solution which solve all the problems we have. It's never happened this way. So as I often say, that every medal has two different sides. One side is advantage, another one is drawback. So advantages and drawbacks of deep learning and convolutional neural networks. So the advantages you already know more or less, but drawbacks are. So first of all, a very large amount of data, of image data, which are labeled, for training of neural networks. So if you have 100 images which are diagnosed and labeled, it's nothing for this approach. So unfortunately, it doesn't work. So you need to go to classical methods, but not to convolutional neural networks, this case, because you need thousands, tens of thousands, preferably hundreds of thousands of images. What is very difficult to accumulate and even more difficult to label manually. since there is no good theory behind this, except this training optimization, how to find the optimal solution for that convolutional filters, there is no theory. And that means, in particular, results of what you are doing basically very often unpredictable. So if you want to know what's happened with this modification of that, you just need to run it. It takes time, you run and you look, wow, that's got better, or unfortunately it got worse, etc. So almost no way to predict the result, because no theory so far. So as a consequence, it's a strongly empirical area, I would say. The next drawback, which is sensitive for biomedical image analysis, is certain degree of stochasticity, which is always related to this, paired to this approach. So even if you start running training with exactly the same training set, you will end up with a little bit different result, because this stochastic process, there is no predefined things. The variation could be small, but it could be not. So it's not good, because in one training you can get that result, in another one you can get slightly different results. So the question then is, what is the truth? What is true result? That's another drawback. It's not very important right now, but it still exists. So there are some other problems, but we will consider them later on. So that's the reading list. So you can stop video right now, look to that list, or you can just type keywords in Google and go immediately to the topic you are looking for, at. So this is the last and the most important slide, because this is the end of module 10 pre-course, which is called Deep Learning. And I'm pressing the button. Thank you very much indeed, and see you during the summer school.